Alright, that one was just a joke. I actually built this one second. For our assignment in digital logic, we were asked to build a counter, and that was not actually it. This one was actually the one I built initially. This one actually counts up from 0 all the way to 15, which I realized was not actually what the assignment asked for, so I had to redo the entire thing. But of course, I kind of already had a base for what I was doing, so this one ended up a lot smaller and a lot nicer, if I do say so myself. This one I tried to plan out to be a lot more compact than that one, and the output for this one I think ended up quite a lot better. So here we have our starting circuit. This basically just starts off the counter. Unfortunately, like the other one, this one does not necessarily start in any particular position. In order to do that, I'd have to add a lot more logic gates to basically reset each of these flip-flops, and that would be big no fun. So I figured I would focus on it just doing just the one thing, which was loop. So when we start this off, the clock over here, which is set to the same timing as the other one over there, this one goes off. This yellow circuit is entirely dedicated to the clock. And as you can see, these are our outputs here. If we look at them from here, you can see that they're counting down in binary. 1, 0, and back to 5, then 4, then 3, then 2, then 1, and then 0 again. So let me just save a little bit of my frame rate here. My computer is not in a condition to actually do any sort of recording, so I apologize for that. To kind of give you an idea of what we're looking at here, these blue circuits are all T flip-flops, which is essentially what a counter calls for, even though we were asked to do it in JK flip-flops. The only difference between a T flip-flop and JK flip-flop that I am aware of is that a JK flip-flop has two inputs, and a T flip-flop just joins those two inputs. So either way, you can see that a T flip-flop in fact does work for this circuit. This light blue is our outputs, and I use that anywhere I needed to kind of separate outputs. Let's see. These orange circuits have to do with the logic concerning how we count down by 1 each time, and then how to overflow into 5. So to count downwards, we need this orange circuit, which combines the outputs of the first two T flip-flop bits. Here we have an AND gate, that's this piston right here. Basically, if the piston is extended, which, the signal has to be on, then it allows this redstone to go through. So basically both sides have to be on, it's an AND gate. And that goes into the input of this last bit. Normally we would string up a bunch of these together, and I can actually show you how that works over here. So each of these pistons also does that exact same process of extending to allow the redstone to go through, just to kind of show you. And you basically just string up a bunch of these in a row. Of course, the difference between a count up and a count down is that instead of using the output, we use the inverse of the output, which is over here. Basically, this is our normal Q output, and this is our not Q output. So when this T flip-flop is off, or when Q is off rather, this turns on, and that goes for both inputs to this AND gate. With both of those on, this T flip-flop will flip basically when both of these circuits are off. So if we subtract 1 from 4, then we end up getting 3, where both of these will turn on and this one turns off. The only other part of the circuit to mention is the part that causes the underflow to go not from 0 to 7, but from 0 to 5, and that's this other orange part, which is basically an OR gate. So if either of these outputs, and this is just Q, this is the actual output, not inverted output, we OR these together with this redstone here. If either of these outputs are on, this redstone turns on, and then we bring that into an AND gate here, where this AND gate is also attached to the output of the first bit. First bit has to be on, and then if either of these other two bits are on, this turns off. And that was just, that was a bit of fancy Boolean algebra to figure out how to make that work correctly. Originally, I just, basically what that logic does is it says that if all outputs are off, then we basically want to flip both the first and the last bits, which is normally what would happen on an underflow anyway. But we specifically don't want to flip this middle bit because then we end up with 5. And that's what this AND gate does. Basically, if either of these bits are on, we do want to allow this, but otherwise we don't. And then there's just this whole mess of wires over here, which basically decodes the binary signal into decimal, and then decimal into the various segments on this display, which I have hooked up here. So let me go ahead and activate this. I designed this to help prevent lag by breaking the signal when I didn't need the display running. But as you can see, if it will actually load correctly, 5, 4, 3, 2, 1, 0, and then back up to 5. So that is the actual counter I made. I realize that it's really compact and it's hard to make a lot of sense of this, but ultimately you can look up things like decade counters online, and you should get a sense of what happens. Basically, you know, decade counters essentially try to read the binary signal and basically say, okay, if this first part's on, the second part is off, and this last part is on, then we need to reset everything to 0. So basically just sets the logic for that. And here we go. This does exactly what the assignment asks for, and it actually does it in a semi-electrical way. So hopefully you guys liked this. I sure had fun making it, although a lot of frustration as well. But thanks for watching, and I hope you had fun.